So these values L, I peak, IRMS, these are the values that will be known to me after doing some analysis on the filtering circuit or on the DC-DC converters, or if the inductor is being used in any other application. Through the analysis of that circuit, I will get the value of the numerical value of the inductance, the peak value of the current that will be flowing from that inductor, and the RMS value of the current from that inductor. And this KCU, it is a scale dependent factor, and it can be achieved between 0.4 to 0.7 when using by hand. So if you are winding this copper wire by hand, in that case you can it can vary between 0.4 to 0.7 if your skill is very good and you are being really careful in the winding of this inductor. You can achieve up to 0.7. And if you want to further improve this copper fill factor, that can be achieved by some advanced machines. Using some advanced machines and well controlled machines, we can achieve we can wind and this copper wire over that core, and we can achieve up to 1 factor. Copper fill factor is equal to 1 or very close to 1. The next, GRMS and Bmax, these two parameters are material dependent. GRMS is dependent upon the type of wire that I will be using for winding. This Bmax is dependent upon the material of core that I will be using. Bmax is taken as 0.2 Tesla for ferrite cores and 1.2 Tesla for silicon steels. And ACAW, also known as area product, AC is area of core and AW is the area of winding. They are the geometric parameters of core. So these are basically the parameters that that I want to calculate or determine through this equation. This L, I peak, IRMS, all of these values, they are known. Now KCU, you can assume any value between 0.4 to 0.7. GRMS will also be known to you. Bmax will also be known to you. The only unknown left in this equation will be ACAW. So by calculating the area product ACAW, you can find you can select the specific core. So there are some other things related to this inductor design, that is the air gap design. So to ensure that the core does not go into saturation at high currents, we need to introduce an air gap as well between the legs of the core. So phi max is equal to Ni over R. This R is reluctance. Bmax AC is will come in place of this phi max. So Bmax AC is equal to Ni over reluctance, and finally I will get this reluctance. Reluctance is equal to Ni over Bmax AC. The next is to calculate the reluctance of this air gap. Reluctance is equal to summation of all the air gaps that will come in the path divided by mu naught AC, or summation L max is L air gap is equal to R mu naught AC. So here R is the reluctance, L air is the length of air gap, and mu naught is the vacuum permeability, which is equal to 4.2 × 10⁻⁷